Okay, so what we're going to look over today is we want to go a bit deeper into the object discussion, which is tied to the function discussion. And we want to, like I said, we want to talk about asynchronous programming. And we're going to talk about some support stuff because much of our code, or some of our code, is going to be run in the browser. Until now, we've run it in the console. And the context is a bit different, right? I said that the language is going to be the same, but the objects and everything that I have access to is going to be different. So first things first, let's look at this example which we used to have. And this is a basic object. It's represented as a list of key value pairs. It's just that some of the values of the keys are functions. Right? And this works because we're in a functional language. I think we've seen this example last time. This is really easy to build, but it doesn't have the defect that I don't know who this is. Right? This does refer to my object. However, it has a couple of issues. One of which is I couldn't name this. Right? What is the type of this object? I couldn't tell you without actually describing the whole object. Right? I'm going to say this object has a name property, which is a string, and it has an age property, which is a number, and it has a printme property, which is a function. So it's this isn't going to do. I need a way to actually name the type of this. The second issue is how would I make another one? Right? If I want multiple of these, let's call them persons. If I want a multiple number of persons, how would I go about this? Well, possibly I might make a function which receives as a parameter name and age and returns one of these. Right? It's somewhat easy to do. It's a factory function. It's something we can do in any language. But if I should make a factory function to create my object, maybe the language should have a feature to do this for me, right? To not force me to create a function, factory function which is called create person object. And indeed it does. Right, so this is my function, and this is a constructor function. Now, there's some subtleties to discuss here. Well, I named it with a capital letter just by a convention. I'm not forced to do this. And I noticed this is a function which receives name and age. And one sec. Receives name and age. And it refers to some this value, right? Because if I think about it, I said that the difference between a function and a method is that a method knows who this is, right? Knows who the object it's applying on actually is. Now, obviously, in order to be able to say this.name equals name, I have to have some sort of allocation for the current object. And the way I'm going to do it is with the new operator. And so it's a bit different from other languages in the sense that what I'm actually talking about here is, well, it's ways of calling a function, which we might call functional invocation patterns. So it's ways of calling a function. So if I call a function just as a function, I say it's a function invocation pattern. If I call it in relation to an object, it's a method invocation pattern. And if I call it with new, it's actually a constructing invocation pattern. Now, what's interesting about this function is that if I call it without new, it's not going to work, right? Now, something to note is this thing I wrote at the beginning. Now, what's this use strict? This is an interpreter directive, so it instructs the JavaScript interpreter to give or not give some errors. This ties into the fact that JavaScript is a dynamically evolving language, and the standard evolves, but there's code out there on the internet which has been written 20 years ago and which uses at least some of the bizarre features of JavaScript. And at the beginning, this sort of thing, so calling person without new, was valid, but it did something really stupid, which is it actually created global variables for name and age. Right. Now, this is not, if I call it like this, and I don't put useStrict at the beginning, this is not going to give me an error. But I put useStrict because I want to use modern JavaScript. So if I call a constructing function without the new operator, it's supposed to give me an error, right? It's not going to let me do that bizarre code. Now, something else to note. What happens, so let's ignore what's written further down. Let me just cover it. And think about this for a moment. The question here is how many print me's are there going to be? So what new does, because I forgot to say this, is it's going to allocate some memory for my object, and then it's going to, then the person function is going to be run over that memory to initialize it, right? Okay, so how many print me's do I have? I have two of them, right? So each of my objects is going to have its own print me function. This, of course, is memory inefficient, but even more important than that, by doing this, I'm going to lose some of the flexibility of the language. Because, and we're going to see shortly, I can actually modify types at runtime. But if each object has their own copy of the function, either I need to have a way of finding all these objects, right? Such an object repository, something to find them again, or I'm not going to be able to do it. So the alternate is to do this, which is person.prototype.printme is function. Now what's going to happen here? Well, this leads us a bit to the discussion about inheritance in JavaScript. Obviously, since I have an object-oriented model in the language, I have to have inheritance. But the way inheritance works in JavaScript is a bit different from how it works in, say, C++. Because the first thing we have to note is that what is common between objects of the same type is not an abstract definition, right? So in C++ or in Java or whatever, what's common between objects of the same type, between persons in this case, is going to be an abstract definition, right? It's a blueprint for the objects, which is a class. But I don't actually have classes in JavaScript, even though I have the keyword. So what's common between objects of the same type is a concrete object. It's an object. It's an object that I can edit. And that object is called the prototype of this particular type. And I can actually access it like this, right? So person.prototype, I can write something in it. Now, why is this useful? Because when I'm searching for a particular property on an object and I don't find it, instead of concluding that it doesn't exist, what the interpreter is going to do is it's going to go to the prototype of that particular object and search for it there. Maybe it finds it. Maybe it doesn't. If it doesn't, it's going to go to the prototype of the prototype and so forth until it runs into a prototype which is null. Right. So this is called prototypical inheritance, and the whole mechanism that I've just described is a prototype chain, right? I'm going through the prototype chain, and I'm going from the most specific thing to the more generic thing. Now, if you think about it, this is similar to what we've seen with namespaces, right? Because an inner namespace had a reference, which I couldn't get. I couldn't actually put in a variable, to an outer namespace, right? And if I didn't find something on the inner namespace, I searched for it on the outer namespace, right? So almost everything in JavaScript is represented as objects. Right, so what's going to happen when I call this function is it's actually going to be invoked on each of my persons, so P1 and P2. Let me just run this, so it's 12. It's not here, sorry. One sec. We're going to get to that as well. Right, so my instances were different. Now, what's the last line? Well, the last line is another strange thing, which is being corrected in time, which is the fact that I can write to the prototype by using type.prototype, but I can access the prototype also from a particular object, which is like this, p1.proto. But this property, underscore, underscore, proto, underscore, underscore, isn't actually writable. Now, this is not exactly true, because this is evolving with the standard, and in the latest version it is actually writable, but not necessarily in my version, right? Because I said that the language is progressively adopted, and at some point all of these features from the standard are going to be in my interpreter, but at this point not necessarily. So let's run this again. Let's save this and run this again, right? And notice that my proto has my function. Now, this way of declaring things, by declaring, so to declare a type, to summarize, to declare a type, I'm actually declaring a function which is supposed to be the constructor of that type, right? That's how I do it. But for two reasons. One of the reasons being that they wanted to make the language more familiar for programmers coming from classic languages. And the second, which we're going to see shortly, which is that in this prototype-based approach actually defining inheritance is going to be a bit more bizarre, so to speak. They've introduced a syntactic sugar thing, which is this syntax. Now this says class person something something, right? Now again, I can't emphasize this enough, there are no classes, right? So this doesn't actually define a different entity. What I'm actually declaring here is the same thing we've seen in the previous example, right? So whatever's in constructor is actually the body of that function, which was called person. And see, it's the same. And print me is going to be a method defined on the prototype of person. Make sense? So these two things are, in terms of what's happening in behind the scenes, are identical. Now, something which I've omitted is the fact that notice something strange here, which is I've declared these persons, and then I've added the function, right? That's because what I wanted to showcase here is because I can actually modify the type even for objects which have been already declared. And how does this work? Well, whatever the object might be, when they search for print me, they're not going to find it on themselves. So they're going to go to the prototype. Now, if I call if I call print me before this line, there's not going to be a print me on the prototype before these lines. There's not going to be a print me on the prototype. But if I call it after, there is going to be a print me. So I'm going to find it and be able to run it. Make sense?
So I have a question. How do we define the prototype inside of where we define to make the image? So up top, can we change the prototype in there?
No, but we can actually define. Sorry, 1 sec. We can actually just declare it after it. I don't have to declare the prototype, by the way. The function already has a prototype. My type defined with the function already has a prototype, but it's just an object. Right? So it's not dependent on me defining it. However, the reason why I put it here is to show that we can define it afterwards. Right. So let's get back to our class example. So the same thing works the same way, right? So it's basically the same. But the implication here is that even though I've declared my type with the class structure, I can actually still modify the prototype, right? So if I were to do something like like adding a new function, and let's say I did it at the end, and I try to call it, this is still going to work, even though I started with the class structure. Right? So I could still add behavior to it. Now this is very useful, but it's actually useful in more complex examples. We're going to see some of them and see what we can do with it. Now, the second thing we want to do, well, I said I have inheritance. Right, so this is inheritance, but done the functional way. To see why I would possibly want a different syntax. So I have a parent type. It has some do parent stuff. I have a child type. And then the child type, what I want to have is I want to have this A, right, which was from the parent, and I also want to have one of my B things. And in other languages, what I do is I call super, right? Does this seem familiar, right? I'd call the constructor of the parent with super or something similar. And maybe it's another keyword, but the concept is the same. Well, this is what I'm trying to do here, but actually it's a bit more complicated, right? Because let's see what super does. Well, super actually is going to take the code of the parent's constructor and it's going to run it over the child instance. Right? I have to initialize something in the child. And this is exactly what I'm doing here, but it relates to the fact, if you remember, that methods are actually functions who know who this is. But what happens if I have a function, which I've defined, it's not tied to an object, but I want to tell it who the object is, to turn it into a method. Well, if I want to do this, functions are actually represented as objects in JavaScript, and they have more, but let's say 3 methods. And 2 of these methods are call and apply. which have similar behaviors. The only difference being that if I use apply, the list of parameters has to be sent like this. So what I'm doing here is I'm calling the parent type function, but I'm telling it just for this call that the object it's being called on is the child. Right? Make sense? So, I can take a function from an object, disconnect it from the object. I can reconnect it to another object. We're going to see this in an example. But generally, I can always attach a function to a particular object. And this is what I'm doing here. I am running the constructor over the space of the instance child, the instance of the child. Right? Thus calling its constructor. But see, it is a bit less intuitive. Maybe I'd like a better syntax for this. And we'll see it immediately. Now, this is something else, which is I said that the prototype of the child prototype is a parent. So the structure I've created is all the children have a common object, and the prototype of that object is the parent. Such as if I add a method to the parent, I'm still going to get rid ultimately. What happens if I have a method on the parent and I actually define the method with the same name on the child? Yeah, it's going to stop at the first one found, so the child. So that way I can override behavior which was defined in the parent if I so need or desire. Right. So let's first look at this, and this is going to be a bit of an adventure with functions. So let's first run 14.1 in this shape. Right. So see that the child actually has access both to the behavior defined in itself and the behavior defined in its parent. Right, so we have this O2, and now we have this function. And this function is just a function. Right, it's not defined on an object, it's a function. And if I call this function, what's going to happen? What do you think is going to happen? If I just call it, I say, I do this line. Yeah, they're going to be undefined. I don't have any of this. It's I can't get them from anywhere, which means, well, I have it here. Undefined, undefined. Okay, so that's not going to do. Probably it's not useful in any fashion. But to explain the idea of the constructor of the parent, I can do this. So the function is an object. It has a method called call. So I can call it and pass something to use as this. So in this case, it's going to, I pass O2, and O2, I think it has 2 and 3 as parameters. So it's going to be temporarily bound to that O2. So just for this call. This doesn't change the function in any fashion. It's just for this particular execution of the function. This is going to be O2.
So every function has like a phantom variable in an object.
Yes, you can consider it like this. But this one doesn't have it. And it can't actually get it. But what I can do is, based on this function, obtain one which is permanently bound to a particular object. This is the third method that the function has, the function object has. So I have call and apply, which are basically identical. And then I have bind, which is going to allow me to do this permanently. So we have F1, and I can't actually make F1 always have this. What I can do is create a new function which has this defined. Right, and if I call F2 right now, just like this, I'm going to see that it is bound. It is bound permanently to it's 1, so it's 0 and 1. Okay. Now, if I think about how bind works, well, we're going to see one example with functions before continuing. We talked last time briefly about memoization, right? Which is a function remembering what it did previously. And I said that we can actually write a function which does abstract memoization, which means it takes any function and it does some stuff and returns a memoized version of that function. Right? So this is somewhat what's happening here. So bind, what bind is going to do, it's going to return a version of F1 which knows that this is a 1. Okay? Let's explore this a bit. Let me just see what the next example was, so we don't. Right. So let's explore this a bit. So I'm going to go to a different example. I don't know why I put it here, but you know. And let's go to abstract memoization. Right, and this is a function which remembers everything it was called on. Now, something to note, of course, this doesn't make sense for all functions. This isn't useful for all functions. It doesn't make sense for functions which don't have stable results. That means they give different results depending on something with the same inputs. In order to memorize a function, you have to have the same results for the same inputs. And it may or may not make sense depending on a particular trade-off, right? So I'm wasting memory to get processing speed. And this maybe makes sense, maybe it doesn't make sense, right? If I have a function which is the one down there, right? So I just add 3 numbers, this is useless to memorize. Because adding 3 numbers is actually faster than going through 2 functions. You know, it doesn't actually make sense. However, I can easily imagine stuff for which this does make sense. Right, so let's look at the structure a bit. So in order to, so this is the principle that Bind had. In order to have this function remember its state, it has to be closed over something. So it can't actually be just declared, it has to be returned from another function. Because remember, when I return a function from another function, it closes over, right? It keeps alive the namespace, the containing namespace.
The context.
Yeah, the context. And in this case, it was an object which I called cache for lack of imagination, just because it's suggestive. And now I have to wonder, okay, so if I want to find some results, how would I find them, right? Based on what? Well, I have, first of all, I have to have this memoize thing has to cover any possible function. So I'm going to write the prototype like that. So function args of any number of arguments. That is an array, args, and I can actually convert it to string with JSON.stringify, and I can use that as a key in my object. Right? So just I can remember what was called. This is going to maintain the order of the elements in the array, so I'm fine. So if I find the key in the cache, I'm just going to write something to the console, but if I don't find it, I'm actually going to run the function I'm memoizing and store the result to the cache. This is a naive example, obviously. Generally, even if functions have stable results, they're not permanently stable. There has to be some logic which expires them. But for this, it's going to be fine. So what I'm going to do is, given any function, in this case add stuff, I can pass it through memoize, and I'm going to get a version of that function which does something else, which is, in this case, it remembers its result. So what we expect to see here is that 1, 2, and 3, the first time it's going to be saved. This one didn't exist in cache, 2, 2, 3. So I have to run the function, see what the result is, and then save it to the cache. But the second call to 1, 2, 3 shouldn't be calculated. Make sense? Right, so it says found it in cache, and it tells me 6. Which is what I initially calculated. So here I calculated, but here I didn't. Let's see another example of this functional behavior, which is a function timer. Again, it's a naive example in the sense that timing function, so given a particular function, if I wonder how long will it take to run, this is a profiling logic, so to speak. So I can monitor my functions or particular functions to see if they cause any problems under specific conditions. But obviously, it's not going to be like in this example, it's not going to be written to the console because that would be useless in real life. Nobody's going to look at the consoles to see which function is long running. It has to be written in a log. It has to do something else. But for our purposes, it's enough. So again, I have a function returned from another function. And this one, which is getTime, is going to add some behavior. And the behavior in this case is I'm just going to write stuff to the console. Write the execution time. The way I get the execution time is I get the date, which is the current date before executing and then after. Now, something to note is that the date object in JavaScript doesn't have enough granularity for this, right? So I can get milliseconds, but if I run a trivial function, that's way less than a millisecond, right? So I probably have to have some mechanism to get time, which is going to be a lot more granular, something to tell me microseconds, not milliseconds. So in this case, I cheated a bit, and I just artificially made my function take a second. take a second, right? And then I write this. By default, it's going to write 1, I think. And let me just go there. Now, something to note is I don't really care about function timing or necessarily about memoization. What I care here is that I can overlap, I can wrap any function in any additional behavior. See what I'm saying? I mean these are just examples. They're not really all that important. The mechanism by which they have been built is important, but they are not. For example, this function is useless. You have to have a bunch more stuff for this to be useful, right? You have to keep the results somewhere, to calculate statistics on results, and to have a better way of timing. So, but the idea is there. Now we have one more advanced example, but we're going to get to that later. So first, let's continue with our discussion about classes. Let's see where we have some inheritance. Do we have some inheritance? Yes. Right, so this is the same example that we had earlier, but it's written in a different fashion. I no longer have to call the parent constructor with call. I no longer have to do any of that stuff. So I said class and parent type. I created a parent, but this time, if you see, it's a lot easier to read. Of course, I have to remember that behind the scenes, it's the same thing with the parent constructor being explicitly called and so forth. I just don't have to write it. So I can do some child type extends some parent type, and this affects the prototype. And if I want to call the parent constructor, I can just use super. Right. Now, a couple more things to note. If I look at do child and all that jazz, I have to wonder what kind of functions these are, and they are functions defined with function, just like in the previous example. Okay, so it's just easier on the eyes. Right, so this still showcases what I said, which is even in the syntax, I can actually decorate the prototype still, and I can do what I could do in JavaScript at any point. So I can change a type and so forth. Before going back a bit, so let's run this. Let's get back to where we were. And see that I managed to do everything. So what I did at line 28 is what I did previously. That is, I added a new function to the prototype, and this is something I have available even for existing objects. And what I did at line 32 is I actually replaced the function on the prototype. Right? So I replaced it with something updated. Maybe I added some behavior. Maybe we can't actually. We can't actually tell from this example what I would want to do, but I can replace the function. Now, to look at this class syntax, I have a couple more things to show you. One of them being this bit. So notice that I have a structure which is a bit different. The things written at the start are going to be properties on the object, right? on any object of this type. So A, which doesn't come defined, B, which comes defined with a 1, it has a default value, and something which says sharp C. Well, what's the difference here? Well, sharp C is going to be private, a private field of my objects. Right? It's not accessible directly. Okay?
Is it protected?
It's private. It's there's no protected. As of yet in JavaScript. Right. Maybe at some point, but there's no protected. So the first things are public. The third thing is private. Okay, so in my constructor, I have to instantiate A, presumably to make sense. So this dot A equals A. For B, I've written, okay, so if you give me a B, that's fine, I'm going to use it, but if not, I'm going to keep my previous value, right? Because I had a default value. And for C, I put some value, is going to be, I just put a 3 here. I could have used a different thing like C here and put it there. Now, this print method is just for debug purposes, but this is the interesting bit. So I have getters and setters. So I have property syntax in JavaScript, and this is the property syntax. In this case, I define a property which is called C, which mediates the access to my private field. Right? So the getter, getC, is going to just give me the value, but for the setter, I have some conditions. So you can't actually, the access is controlled. You can't actually set C, set sharp C to something lower than 1. It's arbitrary, but I could put any condition there, like I would in any setter. Now, how do I use this? Well, the way to use it is their property accessors, so I can just use them like this. Right? In this case, nothing's going to happen, right? Because the setter says that if the value is less than 1, I don't actually update it. So if I run this, I can see C is not being set to -1, right? Because that's the controlled access. Right, so I have encapsulation as well. So I had inheritance, I have encapsulation, and because I can define a function of the child which is going to override the function of the parent, I have a sort of polymorphism. Right, what else? Well, we said that we can declare stuff in JavaScript with var, with let, or with const. And I don't know if we investigated this at this particular instance of the course, but I said that const doesn't actually make stuff constant, right? It makes stuff constant if it's a primitive, but for objects, it makes the reference constant. You can't reassign the reference, but the object is not constant. Now, talking about this constancy business, we have to think about two kinds of constancy, right? Because just like for undefined in JavaScript, I can modify the value of the type. So I can think about, if I want to somehow make an object constant, I can think about making the type constant or the type and the value constant, right? It's there's two different concerns that I might have. Because for any object, by default, I can actually modify the type. I can add additional stuff. So the way to do this, so we have something here, is I have two methods on object, which are called seal and freeze. Now, I encourage you to look over objects and see the whole gamut of methods. There's a bunch of them. But what seal is going to do is it's going to make my type constant, so I can't actually add properties or change their nature. While freeze is going to make my object immutable, right? It's going to be constant in the sense that maybe we'd intuitively think about it, so I can't change anything about it. Now, this is going to be something, let's say, soft, in the sense that I'm not going to get any errors, just the properties are not going to be updated. Right. So let's see what this is. So here I seal the object. After that, I try to change the value of b. This should be possible, right? Because seal doesn't actually make the object immutable. I just can't put properties, right? And it's this line. Here I try to write C on the object, but the object is sealed, which means that object.c is going to be undefined. Whilst here I froze the object. And then I try to change the value of b, and I notice that it doesn't happen. Make sense?
So if seal, we can change the values, but we can't change the...
Yes, you can't change the structure. Now, the reason I'm saying you should look at object is that, apart from the fact that you can say object.b is 5, right? You can actually use a more complex syntax which says object define property on this object and the properties of that property. It's you have a bunch of complex methods to actually do object rearranging at runtime. Now, but talking about object rearranging at runtime, I want to show you another example which is interesting. Now, this is a bit further than we wanted necessarily to go, so it's not something we're going to use, but it's interesting to be aware of it.
I have a question.
Of course.
What are some situations in practice where we actually use the keyword class in a web app? Because if we want classes for safety, just use TypeScript. So what do we have?
No. It's so you use for example in React traditionally or previously, components used to be defined as classes. They're just a way of representing things. Now, in let's say modern React, they're not defined as classes anymore. They're defined as functions with hooks. Let's not get into that at this point. We're going to get to React somewhat further on. So the idea is that that is where you would have used this. And if you make your own component framework, or if you run into a component framework which defines stuff like that, you would use classes. So classes are just an easy way of encapsulating, of grouping behavior and code. For example, let's say I have an application in modern React, so the components are going to look nothing like classes, they will look like functions. However, I want to get data from the server, and let's say I decided to have my own data store, right, which has some logic. I don't know. Maybe if you made a request in the last minute, I'm giving you a cached result or something. Because I know that, for example, I can't actually do updates faster. For example, if I want to have the stock quotations from BBB, right? They actually update them every 5 minutes, I guess, for the free tier. It's something like that. I don't know the details, but right. So I would represent this. This is a thing which has state, right? Which is the previous value I've taken from the server I'm communicating with, and has behavior, which is make a request to the server. Right, so this would be representable as a class. So the limitation that you're going to have, when to use which, right? So the limitation that you have when you're using functional states or closures is that you have one function which has its state. But what if you have multiple functions which somehow operate on the same state? Right? This is where you use the objectual representation. Now, which one of the two you pick, right? So if you write your objects just with function, or you write them with class, it's a matter of personal taste. Because there's no difference. It's syntactic sugar. That's the definition of syntactic sugar. You could write it both ways and get the same result. Make sense? But that's where you'd actually use OOP, right? When you have to group complex behavior with state, not just an item of behavior with state. Also, it's readable. The more complex the more complex the project you're working on, the more this becomes a fundamental requirement, right? For things to be understandable. When you pass hundreds of thousands of lines of code, you know the joke, right? The programmer looks over code and he says, "Who's the idiot who wrote this code?" And then remarks that it was himself 6 months ago. Right? That's the definition of. Right. Okay. Let's see a couple more things for objects, and then we're going to talk about asynchronous programming, which is what I told you. So this is going to be an example which is a bit stranger. Please ask me if I go off the rails completely. But the idea of an active record is a thing which wraps a collection. Right? Only it does something else. So it's in our case it wraps an array, but maybe it wraps a set, something which is collection-like. But what an active record does is when you try to access a non-existing method on the active record might decide to generate it for you at runtime. The typical case is this. I have a collection of objects, they have the same structure, and let's say they have fields A, B, and C. And an active record in its ideal form, although I haven't written this explicitly, is going to allow me to call find by A, find by B, find by C, find by A and B, find by A and C, all of these without me writing them, right? Any condition. Now, obviously, the condition part would be a bit more complicated because we have to actually write a parser. If you want, I can write the example, but we're not and show it to you. But we're not going to see it here. It would take too long. But we can at least do find by property. Right. So what I have here is I have a regular property, and I have the collection I'm wrapping. The regular property is just for demonstration purposes; is not actually useful. And this is my collection. And my collection has a bunch of objects which have the same structure. They have name, age, and job. Okay? Now, what I'm going to do here is, let's see, I want to do this. find by name. But I don't actually want to write it. Maybe there's a bunch of them. Maybe the objects are really complex. So, first of all, I made an object. Where did I make an object? Which is an active record. Now, so reflection in JavaScript is really easy to do, and you can do it at any point, right? You can do object.keys on some object. You can do for property in object. That all works. But there's also, let's say, more advanced reflection features, and these are tied in this case to an object called proxy, a type called proxy, and a type called reflect. Now, reflect actually checks or reads things from an object. Right? It tells me if it has a particular property, the type of that property, the other characteristics of it, if the object is sealed, that sort of stuff. Whilst proxy is going to wrap an object so that any call I do to my proxy is going to be forwarded to my object. Make sense? Just like proxies in networks, right? When I make a request to the proxy actually pretends to be whatever is behind it and forwards the request to the server. Just like this, it works just like this here. So let's see our proxy, right? So our proxy, whenever I call something on the proxy, presumably it's going to get to my active record. So to create a proxy, I have to have an object and some sort of definition of this forwarding behavior, and it's this record handler. And this is interesting because what's here is whenever I get something, so the concept of accessing the property. Get is the concept of accessing any property on this object, right? So whenever I get something on the target, a property on the target, if the target has the property, so if reflect has, then I just access it. It's fine. I don't want to manipulate anything. But if the target doesn't have the property, we're going to construct it. Now let's think what the properties we're accessing. We're accessing find by name, right? For example. So how is this? It's an operation, then some sort of relevant stuff, byte, which is just, we wrote it just so we have a nicer feel to it, and then a condition. Our condition is, in this case, it's minimal. It's name equals something. But we could presumably build more complex conditions, such as find by name and age and job. But that would involve writing something to understand all this and business. So we didn't do that. However, whenever we get a property we don't know, we try to parse it. And the parsing is going to give me a command and a condition. Now, if the command is find, that's because we have a minimal active record and the only thing we're supporting is find, then we're going to return the elements based on the condition. Right. So whatever the condition was has to be equal to the value we're passing. So in this case, we can do find by name n, and let's see if that works. Ta-da! It worked. Right, so this again is not really interesting in itself. What's interesting is that you have this sort of mechanism at your disposal. Right? You can add behavior to objects, even objects you don't control. Right? This might be an object I don't control. I can just wrap an object in a proxy, and I can do this. Now, the last thing we want to see about objects is something which we can do but generally shouldn't, which is this. So I said that I can extend types at runtime. And this also applies to fundamental types. So I could possibly go to the string type, which is a fundamental type, and I could add behavior to it. In this case, the behavior is pretty dumb in the sense that it's a useless function. It gives me the initial letter. But I could definitely imagine some cases where this would be useful. To give an example from real life, let's say I have a database, the database contains records, the records have a key which is not a number but rather a UUID, it's a complex thing. Now let's say the data, so whatever I'm transmitting over HTTP is going to be strings. That's what HTTP transmits. But database has a representation of that ID which is a bit more complex. It's an objectual representation. So I might put this conversion function to object ID on the string. Obviously, I wouldn't put this one, but let's see it in action nonetheless. Right, and it gives me DS. So I've managed to extend the behavior of my string. Okay, so that would be our tour of objects. Do you have any questions about this? Anything? Does this whole object representation make sense? And like I said, if you think about it, it's actually simpler than the classical representation. It's a lot more powerful and it's simpler. Okay, so let's continue. So first of all, let's get back a bit to the browser, and we're going to first look at some HTML. So we're going to continue our tour of HTMLs next time because we actually don't want to focus on this today, but just so we don't talk about things which have not been discussed. Let's go for the simplest HTML. Now, my simplest HTML, no, it's not this one, it's 3. This is something with static properties. Has some text in it. Now, if I look at the structure, let's see a bit. So HTML is a markup language, right? Markup language, it's called markup language because it's similar to, for example, when I underline stuff on a book, I mark it up. Right. Now, the problem I'm going to have when I mark up stuff on a book is at some point, if I want to have a lot of semantic content, I'm going to run out of colors. Or I'm going to run out of colors which can be distinguished by the human eye. So that's not really a practical idea. So, but if I think about marking something on a book, what it's actually is like putting the text I'm marking up between some parentheses, right? And the parentheses mean this is important, or this is, I don't know, a headline, I don't know. Now, this is what's happening here. So I have an open parenthesis and a closed parenthesis. And everything that's between them has some significance. In this case, it is HTML. It's a more generic thing. Now, if I look at the file itself, it has two fundamental parts. So it has the head part, that is stuff I am not showing directly. Right? It's support information. And it has the body part, which is stuff I am showing directly. I'm going to see in the browser. Niche text. Notice that in the head part, what I did is I gave information about how to read the page. For example, I said meta char set UTF-8. So the characters in this page are UTF-8. Right. Now, this is not necessarily, we're going to go back to HTML shortly. This is not what we're interested in. What we are interested in is the fact that HTML has a tree-like structure. And I said that previously that whenever I describe a graphical user interface, I would probably describe it as a tree, right? That's how it works. It's I would even verbally describing it, I would get to a tree-like structure. So this is what I have here. So the browser read this linear text file and it built a little tree. Now, how does the tree look like? Well, it's actually made of some objects, and the objects are going to, the tree is called the DOM, Document Object Model, because it's made of objects. And the objects have almost the structure I think about when thinking about defining a tree. What is the structure I think about when thinking about defining a tree? Well, each of my nodes is going to have some content and the collection of children. If a node is a leaf, the collection of children is empty. Make sense? That's the simplest way of defining a tree. And I have a bunch of these nodes connected. Now, something which I'd expect to have here is a collection of children. Right? Now, this collection of children contains all other objects such as this one. But notice that before this, I have another collection which is called child nodes. That's because the browser has to keep track even of the things which have not been explicitly put into any tag, such as this text, because it has to draw them. Whilst I can't access the text directly as an object, the browser still has to have a little rectangle which contains the text and put it on the screen, right? It has to keep track of it. Right, so this would be, we're not going to go deeper in HTML, but look at these tags again. Well, my tags, so my tags are a solution to the fact that I wouldn't have enough parentheses. But tags themselves, what if I have some text which is going to, so let's say I have a tag containing text, and one of the tags has to contain red text, one of the tags has to contain blue text, and am I going to create tags which are going to be the blue tag, the red tag, etc. It seems counterintuitive. So what I'm going to actually do is I'm going to use some attributes. So these tags actually support a list of key value pairs, and I can write them like this, so they're inside the tag. And some of these attributes that I might have on a tag are general, are global. And one of them is ID. This is the only attribute we're going to need today, but you know, I just said I just thought I had to make an intro. Right, so this is the idea. Now, in the browser, I said that the language is asynchronous. So let's first look at events in the browser and then look at the variants of asynchronous programming I was talking about. So first things first, I said that JavaScript, out of the fundamental technologies present in the browser, is going to handle the behavior. How would I define behavior? Well, if I define it with my own words, I would say something like, when you click a particular button, something happens. Right. So this is actually the description of an event model. And notice that I can get element by ID. That is the attribute, which was the global attribute called ID. The ID is supposed to be unique, so this is going to work out. And first things first, whose document? Well, I said that depending on the context, the interpreter is going to create some global objects. And the global objects are going to vary. They're not the same in the console or in the browser. But in this case, probably I have an HTML document rendered in the browser, right? And that is something which is accessible through document, and this is the root of the document object model. Make sense? Right. And it has a bunch of methods, many of them allow me to search. And in this case, search in your DOM for something with the ID something, D1, D2, D3. Okay, so first things first, I get D1, D2, D3, and for each of them, I say add event listener or on click. Now, the on click variant is the old variant of in JavaScript, and it's a bunch of properties in which you can put a handler function. And they're all written like this, strangely, because they're not camel keys. Right? So it's on click, on focus, on blur, there's a bunch of them, on key press. If I look at any object in the DOM, I'm going to eventually know, because the behavior of the browser changed. But the idea is that I have a bunch of possible properties, right? And these are not defined here. And I can put a handler there. But the issue is, one, I can't put multiple handlers with the on-click syntax. And two, it's not intuitive. How would I dispose of the handlers? Right? So I have a more modern syntax, which is add event listener of some event, some handler. And it has a pair which is remove event listener, obviously. Now, all of these functions are functions of events. There is an event type, which contains what is the most generic stuff for events. But obviously, some events are going to have some particular content, such as a mouse event is going to have a position on the screen. A key event, something which a key press event, is not going to have a position on the screen because it doesn't make sense. But it is going to have a key code, something which identifies the key, which doesn't make sense for a mouse. But there is some global event behavior. So if I look at the structure that I have here, D3 is contained by D2 is contained by D1. And something is going to happen here which is called event bubbling. Now, event bubbling means that whenever this is the default behavior, is whenever I click something, the most specific thing is selected. It has the chance to run any handlers for that event which have been registered to it. And then it sends the event to its parent. Now, the parent maybe has some handlers, maybe it doesn't. But anyway, after it finishes, it's going to send it to its parent, and so forth until we get to window. In JavaScript, I can actually do something which is a bit less intuitive, which is I can do event trapping, which is I'm going to start from the outermost parent and go down. It's not really all that useful. Generally, I want to do this bubbling behavior. Generally, if you think about the user interaction, the user thinks in that fashion. So when they click something, it's the more specific thing, instead of clicking the window. Now, let's see what's happening here, because if you look in the console, I click this, and it says D3, then D2. Now, why not D1? Well, I have a method on event which says stop propagation, which is actually going to prevent me from getting to D1. Now, some of the things have default events. One sec. Some of the things have default events, such as when I click this expression is equivalent to get element by ID. We're going to see how this works when we get to CSS. In this case, when I click a link, what happens by default is it navigates to the link. But what I can actually do is do event prevent default, and then add my own behavior. For example, if I want to transform a link into a button or something. So this is just going to write nope in the console, and it's never going to navigate. Conversely, I also have access to my own events. And in this case, what's going to happen is I have two divs. One of them doesn't respond to click, but it does respond to a custom event, which is called alarm. So when I click the second div, it's going to manually create an event and send it to the div that doesn't have clicks. Right? This happens because an object which I can see, which is can respond to events, is called an event target. Now, everything in a web page is an event target. So I can send events to anything. And in this case, I make my own custom event. This is going to come into play a bit later. And the last example I want to show you about events, so we need E2 here. So if I click this don't click me thing, it doesn't have clicks. However, I can click the click me. What it actually does is create an event, it sends it to don't click me, and don't click me writes to the console. Now, the last thing we want to say is this mouse event demo. This is to showcase the fact that the mouse event has additional information pertaining specifically to a mouse event, such as the button I'm pressing. Right? This doesn't make sense for anything else, but it does make sense for mouse events. Now, to get to the other discussion. So, obviously, events are a way of doing things asynchronously. Right? So what other ways of doing things asynchronously do I have? Because it's obvious that events play a fundamental role in the graphical user interface, and the option in JavaScript was to consider that the language is fundamentally asynchronous. So let's say we have a series of operations, and those operations are asynchronous, but they depend on one another. How do I make my code work? Right? So I have F1, F2, and F3. F1 takes some time, maybe an unknown amount of time, and when it ends, I'm going to run F2. This is the logic of my program. So with events, what I might do, so set timeout actually runs a function after a bit of time. So I want to run something when this function ends. How would I organize my code? Well, in this case, I make a custom event. I put some result of the custom event, and I trigger the event. The destination is then going to treat the event as complete and execute the code. But scale this, what you're seeing here, scale it to hundreds of operations. it's going to become a bit hard to follow, right? Now, the second way to do it, of course, this works. I can show it to you in the browser. Right. But notice something. Notice that. Right. So if I want to do something else asynchronous, what would I have to do? Well, I have to trigger it here, trigger an event whenever it happens, and so forth. So not ideal. Second way of doing it is callbacks. Now, whenever I have something asynchronous, what I might do is, apart from the parameters for the task, I might actually send a function as a parameter and tell that task, whenever you finish, call this function. This is a bit better. Notice that I have a parameter here called callback. So whenever this is run, it's going to call that function, and we don't know what's going to happen. But whoever gave the task to us probably, possibly knows what to do with the results. Right. One sec. Oh, it's in HTML, sorry. Right. Result for F0. Now, why did I write the next things? Because, for example, when I call F0, and if I move next here, where do you think next is going to be written? So we can understand the problem a bit better. Is it going to be written before or after result? Before, right. Because I'm not waiting for it. Right, so that's the problem. The problem, how do I synchronize asynchronous code? It's obviously, in this case, it's artificially delayed, but the same principle. Right, so you hopefully begin to understand the problem. The problem is, so asynchronicity is very good for parallelizing stuff, but what happens if I have code which is dependent on the result of that stuff? Right? It's this switch between having an asynchronous perspective and having a synchronous perspective. How do I reconcile these? And now we get to what we were saying. So JavaScript has an error handling mechanism, which is the error handling mechanism that you might find in C++. So try, catch, finally, throw. Right? The only difference is that the type is not called an exception, it's called an error. So it's throw new error instead of the exception. Again, like I would in, say, Java, I can define my own errors by just inheriting that type and extending it, and so forth. So we're going to see that they're going to make an appearance shortly. So the first thing that's going to be happening is I'm going to replace this callback logic with something promise-based. Now let's get back to promises. Now what a promise is a future value, right? If I think about a bit of code, it can be, if I have an expression which I evaluate, it can be evaluated if and only if it is concrete. If I have all the items from it. So if I do 5 plus 5, 5 and 5 are concrete, so I can get 10. But if I do 5 plus future, that's not concrete. 5 is not addable to future, even if future is a future number. So what I can do under these conditions is I can wait for the future to become concrete, because a future value is going to be in one of three states. State number 1 is pending. The only thing I can do while it's pending is wait for it. Then, after a while, one of two things is going to happen. Either I'm going to get a value, and then the future is resolved, the promise is resolved, or I'm going to know precisely that I'm never going to get a value, and then the promise is rejected. Right? I know that I should have an error. I'm never going to have 5 plus a number.
And we can't do that with callback.
No, the problem is, so the reason why promises appear is that callbacks create this, like I said, this continuation passing step. If you think about something with a bunch of callbacks, what's actually happening is, imagine a programming language in which each line tells you what the next line is.
Yeah.
And
It's for syntax.
it's for organizing stuff. So promises are not necessarily that much of a new concept. There's a design pattern, which is an elevated design pattern. That means that it was used on a large scale to organize code, and at some point it just got into the language because it was so useful. If you see what I'm saying. But I can do the same, I can do everything that you can see here, I can do with callbacks. But it's going to be, unfortunately, organized. It's not just that it's going to be ugly, but it's going to be really hard to debug. Because if you think about the callback giving an error, you have a callback in a callback in a callback in a callback in a callback. Right? Your whole program is a stack of callbacks. If you think about the real world example. The real world example is going to be something like this. It's going to be read a file, which maybe you can, maybe you can't. Parse the thing. The file is XML, which means it takes a lot of time to build the tree. Extract some data from the XML and write it to a database. And this is 30 callbacks. Already, you know, I mean, it's not going to work out. Right, so what are promises? Promises are objects which have two methods, which are a then and a catch. Then receives a callback, which is going to be run whenever the promise is resolved. Right, so if the promise is resolved. Catch receives a callback, which is going to be run when the promise is rejected. Now this does look a bit strange, but we're going to be able to circumvent it most of the time. So if this promise returns a future value, a promise, it returns an object built on a function of two functions. Third order functions. You know? Now, but I can think about this stuff as if I would have think about a block. So it's always going to look like that. And I'm going to write my code inside here. And what my responsibility is to call resolve of value whenever I have a success in my operation, and to call reject of error whenever it's rejected. Right? And that's it. And the shape is going to always be the same. So to a certain extent, ignore the fact that I have a function of the third order here. That's just how this design pattern works. If you want to, like I said, I put online some articles which are interesting, but they may or may not be easily understandable at this point, depending on your experience with various languages. Now, what this allows me to do is so F0 returns a promise. The promise, I know, has a then method. So I say F0 then, if I have a result, I have a function of result and I do some stuff. But let's say that stuff also has a promise. Returns a promise. Well, my advantage here is that promises are chainable. So I can write this sort of code. So I'm going to do the first asynchronous thing, then I'm going to do the second asynchronous thing, then the third asynchronous thing, and so forth. And at the very end, I can put a catch. So what this allows me to do is to not treat the idea of failing at each operation.
It's a failure for all of them.
Yes. But this sort of kind of looks like a try catch if we squint. Right? It's try catching. It's try catch like. Right. So, but it's still somewhat uncomfortable. That means that if you write this sort of code, you're going to run into code which is really hard to read. So I have syntactic sugar, which is async await. So this is actually the same thing, more or less. It might not be identical code, but it's the same principle. So I have some functions which return promises. So if I'm in an async block function, I can await promises. So what await is going to do is it's going to wait for F0 to be resolved. Now, the reason why I say this whole thing is a design pattern is that you're going to find this in C#, in Rust, you're going to find it in a bunch of languages. It can be re-implemented anywhere. Right, so what's going to happen here? Well, in this case, obviously, if I'm awaiting, I don't actually have the catch branch. So what's going to happen is an error is going to be thrown, and I can treat it as in any kind of code. Now, in more modern in this JavaScript, I cannot use await unless I'm in an async function. In more modern JavaScript, which may or may not be implemented, you have top-level await, so you can just use await in the global instance. But for example, the Node 20 something has top-level await, Node 18 something doesn't have top-level await. So it's a, let's call it a recent feature. I don't know how to call this. It's not generally implemented.
So for our project, you just use async await.
Yes. Because it's simpler. The only point where we're going to maybe run into promises, we're going to have a course where we're going to, if you have time, we're going to talk about integrating external services. And when you integrate something like Google or Microsoft or whatnot, you might run into some APIs which are written with callbacks, and you can actually promisify them. You can wrap them into promises. We'll talk about that when it's time. But there's one more important thing to talk about. So what I've done is I've taken asynchronous code and I've linearized it, so to speak, in this case. But asynchronous code had a bunch of other advantages, right? So asynchronous code had the advantage of running things in parallel. Did I lose the opportunity to do this by using promises? Because if I did, maybe I should have just used a different language, right? If all I wanted was to make asynchronous code synchronous, I didn't gain anything, right? I just switched languages low key. Well, I didn't, and the promise object actually has a couple of methods, promise all and promise raise. So what promise all is going to do is it's going to receive an array of promises, and promise all itself a promise is going to be resolved when all of them resolve. Right? And I'm going to get an array of results, but they run in parallel, and they're not run consecutively. Well, promise raise is going to receive an array of promises, and it's going to be resolved when the first one is resolved, which may of course mean that not all of them resolve. Right? It's the first one is resolved, maybe another one was rejected, but that doesn't matter, because at least one was resolved. And I can see this, and this is going to be our last thing. So if I look here, right, one done, and then all done. Now, notice something else. One of these, where was it? Async await. One of these actually, instead of doing resolve, did reject. And when the promise is rejected, the execution is going to stop, and I'm going to get to the catch block. I'm going to stop the recording.